The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. So what I'm going to do next is switch gears to one existing compiler, which is the Streamit parallelizing compiler. So the main idea about Streamit is the need for a common machine language. So what you want to do normally is in a language, you want to represent common architecture properties, so you get good performance. You don't do it very high level abstraction, so you waste a lot of cycles dealing with the abstraction. But you want to abstract out the differences between machines to get the portability. Otherwise, you are going to just do assembly for hacking for one machine. And also, you can't have things too complex because a typical programmer cannot deal with very complex things that we ask them to do. And C and Fortran was a really nice assembly language, a common assembly language for imperative languages running on the Unicode machines. Okay, and the problem is this type of language is not a good common language for multi-cores because it doesn't deal with, first of all, multiple cores. And as we change number of cores, it's for example, automatic parallelizing compilers are not good to basically get really good parallelism out of that, even though we talk about that. Still, a lot of work has to be done in that. So what's the correct abstraction if we have multi-core machines? So the current offering, what you guys are doing is things like OpenMP, MPI type stuff. Okay, you are hand hacking the parallelism. What's the issue with that? It's basically this explicit parallel construct kind of added to languages like C. That's what you're working on. And what this does is all these nice properties about composability, malleability, debuggability, portability, all those things were kind of out of the window. And this is why this parallelizing is hard, because all these things makes life very difficult for the programmer. And it's a huge additional burden. The programmer has to introduce parallelism, correctness, optimization. It's all left to the programmer. So what the program has to do in this kind of world, what you're doing right now, you have to feed all the granularity decisions. If things are too small, you might get too much communication. If things are too large, you might not get good load balancing, stuff like that. And you need to deal with all the load balancing decisions. All those decisions are left for you guys. You need to figure out what's local, what's not. And if you make a wrong decision, it can cost you. All the synchronization and all the pain and suffering that comes from making a wrong decision, things like race conditions and deadlocks and stuff like that. And this, while MIT students can hack it, you can't go and treat the Joe programmer to convert from writing nice, simple Java application code to dealing with all these complexities. So this is what kind of led to our research for last 5 years to do Streamit. And what we want to do is move a bunch of these decisions to the compiler. Granularity, load balancing, locality, and synchronization, those decisions. And today's talk, I'm going to talk to you about after you write a Streamit program, as Bill pointed out what the nice parallel properties, how do you actually go about getting this kind of parallelism. And so in Streamit, in summary, basically you have regular repetitive computation in these filters, and this is called a synchronous data flow model, because we know at compile time exactly how the data moves, how much each produces and consumes. And this has natural parallelism, and it exposes exactly what's going to happen to the compiler, and compiler can do a lot of powerful transformations, as we point out, I point out. The first thing is, because of synchronous data flow, we know at compile time exactly who need to do what when. And that really helps transform. It's not like everything happens runtime dynamically. So what does that mean? So what that means is, so each filter knows exactly how much to push and pop that's in repetitive execution. And so what we can do is we can come up with a static schedule that can be repeated multiple times. So let me tell you a little bit about what a static schedule means. So assume this filter pushes 2, this filter pops 3 but pushes 1, that filter pops 2. So these are kind of rate mismatch. It's not everybody producing consuming ones. So what's the schedule? So you can say, okay, at the beginning, A produces 2 items, but I can't consume that because I need 3 items, and then I do 2 of them, and I can consume the first 3, and then produce 1 there, and I have 2 left behind. I do 1 more of that, and now I got 3, and it consumes that and produces that, and then I can fire C. So the neat thing about this is when I started, there was nothing inside any of these buffers, and if I ran AA, BA, BC, there's nothing inside buffers again. So what I have is I am back to the starting position, and if I repeat this millions of times, I keep the computation running nicely without no buffers accumulating or anything like that. So I can come up with this very nice schedule that says here's what I have to do. I have run A actually 3 times, B twice, and C once in this order, and if I do that, my computation keep running. And that gives me a good global view on what can I parallelize, what can I load balance, all those things, because things doesn't change. One more additional thing about Streamit is we can look at more elements than I am consuming. Question?
So how common is it in typical codes that you can actually produce a static schedule like that?
A lot of DSP code has this is very common. Okay, in a lot of DSP code right now that goes into hardware and software, they have very common properties. Mm-hmm. But even things that are not common, what has a very large chunk of the program has this static property, and there are some few places that has dynamic properties. So it's like when you write a normal program, you don't write a branch instruction after every instruction. You have a few hundred instructions and a branch, a few tens of instructions and a branch type thing. So what you can think about it is that instructions that without a branch can get optimize the hell out of them, and then you do a branch dynamically. So you can think about like this. What's the largest chunks you can find that you don't have this uncertainty until runtime, and you can optimize the hell out of it, and then you can deal with this runtime issues, basically branches or control for changes or data rate changes at runtime. So if we have 10-90 rule, if you get 90% of the things are in a nice thing, and if you get good performance on that, hey, it has a big impact. So in our language, you can deal with dynamism, but our analysis is basically trying to find the largest static chunk and analyze. So most of the time, that basically said we start with empty and end with empty. But trouble is, a lot of times we actually can look beyond the number of we consume. So what you have to do is kind of do initial schedule that you don't start with empty. You basically consume something. You start with something like this. So the next time when something comes, 3 things come into this one, I can actually peak 4 and pop 3. So you go through first thing kind of priming everything with the amount of data needed, and then you go to the steady state schedule. This kind of gives you a feel for what you get. This is the neat thing. I know exactly what's going on in here. So now how do I run this parallels? This is something actually Roderick pointed out before. There are 3 types of parallelism we can deal with. So here's my stream programming here, and I do some filters, scatter, gather in here. The first type of parallelism is task parallelism. What that means is the programmer said there are 3 things that can run parallelly before I join them together. So this is a programmer specified parallelism, and you have a nice data parallel, nice representation here. The second part is data parallelism. What that means is you have some of these things that doesn't depend on the previous run of that one. So there's no invocation dependence across multiple invocations. These are called stateless filters. There's no state that keep changing. If state keep changing, you have to wait till the previous one finishes to run the next one. So if you have a stateless filter, assume that is data parallel. What you can do is you can basically take that, replicate it many times, and when data comes, parallelly send it to every data, and it will compute and parallelly get out here. The final thing is pipeline parallelism. So you can feed this one into this one, this one into this one, and then browse across in a pipeline fashion, and you can get multiple things execution. So you have these 3 types of parallelism in here. And the interesting thing is if you have stateful filters, you can't run this data parallel. You actually only parallelism you can get is pipeline parallelism. So traditionally, task parallelism is fork join parallelism that you guys are doing right now. Data parallelism is loop parallelism. And pipeline parallelism mainly was done in hardware. If you have done something like Verilog or VHDL, you will do a lot of pipeline parallelism. So kind of combining these three ideas from different communities all into one, because I think programs can have each part in there. So now, how do you go and exploit this? How do you go take advantage of that? So I will talk a little bit of baseline techniques and then talk about what Streamlit compiler does today. So assume I have a program like this. Nice thing is there are two tasks in here. Program are given, you don't have to worry anything about that. And what you can do is assign them into different cores and run it, neat. And so you can think about a fork join parallels. You come here, you fork, you do this thing, and you join in here. So the interesting thing is if you have a 2 cores, you probably get a 2x speed up in this one. This is really neat because there are 2 things in here. The problem is, how about if you have a lot more different number of cores? And if next generation has double number of cores, and I'm stuck with the program you wrote for the current generation. So this is not that great in here. So we ran it on the raw processor we have. It has a 16 cores in there that we have been building, and this is like running the simulator of that. What you find here is this bunch of Streamlit programs we have. We kind of get performance like basically close to 2. Because that's the kind of parallelism people have written. In fact, some programs even slowed down in there, because what happens in here is the parallelism and synchronization is not matched with the target, because it's matched with the program. Because you wrote a program because your parallelism in there was what you thought was the right for the algorithm. You never had, we didn't want you to give any consideration to the machine you are running, and it didn't match the machine basically if you just got the parallelism, and you just don't do that well. So one thing we have noticed for a lot of streaming program, to answer your question, is there are a lot of data parallelism. In fact, in this filter, in this program, what you can do is you can find data parallelism filters and parallelize them. So you can take each filter, run it on every core for a while, get the data back, go to the next filter, run it on every core while, get the data back. So what you can do is, if you have 4 cores in here, you can each replicate all these 4 times. You run these 4 for a while, and then these 4, these 4, these 4, these 4. Okay? So that's a nice way to do that. So the nice thing about doing that is you have a lot of nice into load balancing, because each are doing the same amount of work for a while. And after it accumulates enough data, you go to the next one, do for a while, and then like that. And each group basically occupies the entire machine. You just go down this scope like that. And so we ran it, so it's even slower. Why? We should have a lot more parallelism, because all those filters were data parallel. So instead of getting stuck with 2, now we can easily run a parallelism of 16, because each data parallelism you can just put it any amount in there. But we are running slow.
Communication overhead?
Yeah, it could mainly be communication ahead, because what happens is you run this for a small amount of time, you have to send it all over the place, collect it back again, send it all over the place, collect it back again. The problem is there's too much synchronization and communication. Because every person at the end is like this global barrier, and the data has to go shuffling around, and that doesn't help. So the other part, what you can do in the baseline is what you call hardware pipeline. What that means is you can actually do pipeline parallelism. The way you can do that is you can look at the amount of work each filters contain, and you can combine them together in a way that the number of filters is going to be just above the number of tiles available. Okay, so now most program has more filters than number of cores. So you combine filters together. So number of filters is just either same or 1 or 2 less than number of cores available. In a way that you combine them, so each of them will probably have close to the same amount of work. The problem is, if you combine, it's very hard to get the same amount of work. And if we assume 8 cores, you can do this combination. You can say, aha, if I do this combination, I have 1, 2, 3, 4, 5, 6, 7, 8 cores, I can get 7 of them. Hopefully, each of them have same amount of work, and I can run that. And then we assign this to one filter and say you own this one. You run it forever. You get the data from guy who owns this one, and when you produce it, this one. And if you have more cores, you can actually keep doing some of that. If you have enough filters, you can each combine them and do that. So we performed, and we got this. Not that bad. So what might be the problems here?
Hardware pipeline?
Yeah, it's hardware pipeline.
Locality. You got to make sure that the communicating filters are close to each other.
Yeah, that we can deal with. I think this build the locality. What's the other problem? There's a bigger problem. Load balancing is the biggest problem, because the problem is you're combining different types of things together, and you're hoping that each chunk you get combined together will have almost identical amount of work. And that's very hard to achieve most of the time, because dynamically things keep changing. Now, and the nice thing about loops is most of the time if you have loop or state, if you replicate it many times, it's the same amount of code, same amount of work, it nicely balances out. Combining different things become actually much harder. So again, parallelism and synchronization is not really matched to the target. So the Streamit compiler right now do 2-3 things. It calls on, I will go through details, calls on the granularity of things. So what happens is if you have small filters, it combines them together to get the large stateless areas. It data parallelize when possible, and it do software pipeline because of pipeline parallelism. I'll go through all these things in detail. And you can get about 11x speed up by doing all those things. So course on the stream graph. So you look at the stream graph and say, wait a minute, I have a bunch of data parallel paths. And before, what I did was I take each data parallel path, did 16-way, and then came or get together. When 16-way came together, when 16-way. Why? I have put too much communication. Can I combine data parallel things into one gigantic unit when possible? Of course, you don't want to combine data parallel part with a non-data parallel part. Then the entire thing becomes sequential, and that's not helpful. So in here, what you found is these 4 cannot be combined, because if you combine them, they become the entire thing becomes sequential. So what you do is you can combine this way. So all those things are data parallel, all those things are data parallel, and even though they are data parallel, if you combine them, they become non-data parallel, because this is actually doing peaking. It's looking at more than one. And so it's looking at somebody else's iterations work. So you can't combine them. So what the benefits of doing this is you reduce global communication basically. And the next thing is you want data parallelized into 4 cores. And this one you can fish 4 ways in there. But the interesting thing is when you go in this one, you realize, hey, there's some task parallelism. Okay, we know there are 2 tasks that have the same amount of work in there. So fishing these 4 ways and fishing these 4 ways and giving entire machine to this one and giving entire machine to this one might not be the best idea. What you want to do is you want to fish it 2 ways, and then basically give the entire machine to both of these, all of these running at the same time, because they have load balance, because they are same thing repeated. And you can do the same thing in here. Okay, so that's what the compiler do that much automatically, and it reduces, it preserves task parallelism. So if you have task parallelism, you don't need. The thing about that is the parallelism you don't need too much parallelism. You need enough parallelism to make the machine happy. If you have too much parallelism, you end up in other problems like synchronization. So this gives enough parallelism to keep the entire machine happy, but not too much. And by doing that, actually we get pretty good performance. There are few cases where this hardware parallelism wins out, these 2, but most of actually this last one we can recover, doing pretty well. Okay, so what's left here is, so this is good parallelism, but and low synchronization. But there's one thing, when you're doing data parallelism, there are places where there are filters that cannot be parallelized. They are stateful filters. Okay, so you can't run them data parallelism, and according to Amdahl's law, that's actually going to basically kill you, because that's just waiting there, and you can't do too much. So I'm going to show that using this separate program. So this number is amount of work that each of them has to do. So this is actually a lot of work. These do little work in each of these filters. So if you look at that, these are data parallel, but it doesn't do any much work. Just parallelizing this doesn't help you. Whereas rest is not, and these are data parallel, and these actually do enough work. Actually, we can go and say I'm replicating this 4 times, and I'm okay. I'm getting actually good performance in here. Now what you have is a program like this. And so if you are not doing anything else, if that we have data parallelism, so what happens in the first cycle, you run these 2, and then you run data parallel this one, and then you run this, and then you run data parallel this one. Okay, and if you look at that, what happens is we have a bunch of holes in here, because at that point when you're running that part of the program, there's not enough parallel. So when you only have 2 things in there, and when you're running this, you can run this task parallelism in here, but there's nothing else you can do in here. And so you get basically 21 time steps each, time units basically run the entire program. But here we can do better. What we can do is we can take and try to move that there and kind of compress them. Okay. But the interesting thing is these things are not data parallel. So how do I do that? So the way to do that is taking advantage of pipeline parallelism. So what you can do is you can take this filter in here. Since each of the entire graph can run only sequential is this has run after this, we can look at the filters running separately like that, and kind of say, instead of running this and this and this, why don't I run these iterations of this one, these iterations of this invocation, these iterations of this one, and these iterations of the next one. And I'm still maintaining, because when I'm running this, even though I'm not running anything data parallel here, because these ones were already done previously, so I can actually use that value, and so I can maintain that dependency. But I'm running things from the different iterations, and so what I need to do is I need to kind of do a prologue to kind of set everything up in there, and then I can do that, and I don't have any kind of dependence among these things. So now what I can do is I can basically take these 2 and basically lay out anything anywhere in those groups, because they are in different iterations, and since I am pipelining this, I don't have any dependence in it. So I end up in this kind of a thing, and basically much compressing here. And by doing that, what you actually get is a really nice performance, and only place that this actually wins hardware pipelining, and this little bit in there. But the rest you get a really good win here. Okay, so what this does is basically now we got a program that when the programmer never thought anything about what the hardware is, just wrote just abstract graph in there and stream it, and given raw, we automatically actually mapped into it and figured out what the right balance, right communication, right synchronization, and got really good performance. And you're getting something like 11x performance. If you do hand, if you work hard, probably you can do a little bit better. But this is good, because you didn't have to do anything. The killer thing is now I can probably take this set of programs, which we are actually working on, is we can take them to cell, which has, depending on the day, 6 cores, 7 cores, 8 cores, and we can basically get to the matching the number of cores in there. So this is really nice. So because right now what happens is you have to basically hand code all those things, and this can automate all that process. So that's the idea, is can you do this, which we haven't really proven. This is our research. Write once, use anywhere. So write this program once in this abstract way. You have to really don't think about full parallelism. You have to think about some amount of parallelism, how this can be put it into a stream graph, but you're not dealing with synchronization, load balancing, performance. You don't have to deal with that. And then the compiler will automatically do all these things behind you and get really good performance. And the reason I did show this was, basically I have one more slide, I think. Yeah, best here. Showed this was, it's not a simple thing. The compiler actually has to do a bunch of work, the work that you used to do before. Things like figuring out what's the right granularity, what's the right mix of operations, what type of transformations you need to do to get there. But at some point we can do we did three things: coarse grain, data parallel, and software pipelining. And by doing these three, we can actually get a really good performance in most of the programs we have. So what we are hoping is basically these kind of techniques can in fact help programmers to get multi-core performance without really going and dealing in the grunge level of details you guys do. You guys will appreciate that, and hopefully we'll think of making, because now at the end of this class you will know all the pain and suffering the programmers go through to get there. And the interesting thing would be to in fact look at the ways to basically reduce that pain and suffering. So that's what I have today. And so this was, as I promised, a short lecture, the second one. Any questions?
So if you've got enough data parallelism, you'll have the same software pipeline chunk on each tile, is that right?
Yeah.
Okay. So if you do that, how does it scale up to something that has higher communication costs than raw? Because you've got all of your, by doing this, the software pipelining, you have to do all of your communication off tile.
So the interesting there right now is we haven't done any kind of hardware pipelining. We are kind of doing, everybody's getting a lot of data and moving in there. The neat thing about right now is even with the SP in cell and even raw, the number of tiles are still small enough that a lot of communication, unless you do way too much communication, it doesn't really overwhelm you, because you can, everybody is nearby, you can send things. They talk a little bit about in cell that near neighborness helps, but not that much. But as we go into larger and larger cores, it's going to become an issue. Near neighbors become much easier to communicate, and you can't do global things in there. And at that point, you will actually do some hardware pipelining. You can't just assume that at some point everybody going to get some data and go to something. So what you need to do is have different chunks that only communication would be between these chunks would be kind of a pipeline communication. So you don't mix data around. So as we go into larger and larger cores, you need to start doing in techniques like that. The interesting thing here is, even though what you have to change is the compiler, hopefully the program stays the same. Right now it's not an issue because our compiler has 10 times more code than the program, so it's easy to train the program. But if you look at something like C, the code base is millions times larger than the size of the compiler. So at some point there will be a switch. It's easier to change the compiler to kind of keep up to date. That's what happened in C. So every generation you change the compiler. You don't ask the programs to say, go rewrite the application. So can you make these kind of things as the multi-cores become different, bigger, have different features, you change the compiler to get the performance, but have the same code base. I mean, that's the goal. That's the goal for portability.
Have you tried applying Streamit or the streaming module in general to codes that are not explicitly, or not very clearly stream-based, but rather but using the streaming model to make the communication explicit, such as like scientific codes, or for example, the kinds of parallelizable loops that you covered in the first half of the lecture?
Some of those things, if when you have uniform, simple communication, can map into streaming. So for example, one thing we are doing is things like right now MPEG. Some part of the MPEG is nicely streamed, but when you actually go inside the MPEG and dealing with the frame, it's basically a big array, and you're doing that. So how do you chunkify the arrays and basically deal with it in a streaming manner? There's some interesting things you can do. There are obviously some stuff that doesn't fit that well. So assume things like kind of a pattern recognition type stuff, where what you want to do is you want to, assume you are trying to, good example, you are trying to do feature recognition in a video. And what happens, the number of features, you might recognize 2 features, you might recognize 1,000 features. And then each feature you need to do some processing. And that is a very dynamic thing. And that doesn't really fit into streaming model right now. And so the interesting thing is the problem we have been doing is we are trying to fit everything into one. So right now the object-oriented model is it basically. Everything has to fit in there, but what you're finding is there are many pieces that doesn't really fit nicely. And you do this very crazy looking things just to get every program to fit into object-oriented model. That doesn't really work. I think the right way to work is there might be multiple models. There's a streaming model, there's some kind of a threaded model, there might be different models. I don't know what other models are. So the key thing is, your program might have a large chunk in one model, another chunk in another. Don't try to come up with, right now what we have is we have a kitchen sink type of language that tries to support everything at the same time. And that doesn't really work, because then you have to think about, say, okay, done, can I have a pointer here? I need to think about all the possible models kind of colliding in the same space.
On the other hand, having sort of a kitchen, the object-oriented model is much more generalized. I mean, it's not the best model for many things, but it's much more generalizable than some models. And having a single model cuts down on the number of semantic barriers you have to cross. In
I don't know, but
the semantic barriers incur both programmer overhead and runtime overhead.
See, the problem with right now is our semantic barriers is object-oriented model plus huge number of libraries. If you want to do OpenGL, it's object-oriented, but you have no the library. If you want to do something else, you have to library. What the right thing would be, instead of trying to learn the libraries, learn a kind of a subset language. So you have nice semantics, you have nice syntax in there, you have nice error checking, nice optimization within that syntax, instead of, because the trouble is right now everything is in this gigantic language, and you can't do anything, and in a program you don't even know, because you can mix and match in really bad ways. Even the mix and match gives you a lot of power, but it can actually really hurt, and a lot of people don't need it. Like for example, in C, people thought it was really crucial for you to access any part of memory anywhere you want. You just can go and just access any program anywhere, anytime in there. If you look at it, nobody takes advantage of that. How many times you write the program and say, hey, I want to go access the other guy's stack from this program? That doesn't work. You have a variable and you use variable. Okay? Yeah, but the thing is, because of that power, it creates a lot of problems for a compiler, because it needs to prove that you're not doing that, which is hard. And also, if you make a mistake, the program says, yeah, this looks like right, it still matches my semantics and syntax, I will let you do that. But what you realize is that's not something people do, just stick with your variables. And if you don't go out of variables, I mean, that's what type-safe languages does. It's probably more of a bug than a feature. And the same kind of thing, having a kitchen sink language, is you can do everything at the same time. Why can't you have a language that you can go with this kind of context? I am in the streaming context now. And I say this is my streaming context. I am in a threaded context. And then what that does is, I have to learn the full set of features, but I restrict what I am using here. That can probably really improve your program building, because you don't have to worry about.
Programmer time because you have to learn 8 languages, right?
No, but right now you have to do it. If you look at C#, it has all these features. It has streaming features, it has threaded features, it has every possible object-oriented feature.
But it's still.
There's a compact central model which covers most things, and then you can pull in additional features and fit them into the model.
I
Like
mean,
if you want to do, you can do pointer manipulation in C#, but you bracket things with you bracket things into an unsafe block, and then the compiler knows in there you're doing really bad things.
But can you do it more than, I mean that's nice thing, because you can have unsafe, but can you have something that this is my streaming part? Okay, can I do something like that so I don't have to worry about others? The key thing is there a way where, because right now my feeling is, if you look at the object-oriented part versus all, so if you are doing, for example, Windows programming, you can spend about a week and learn all the object-oriented concepts. And you have to spend probably a year learn all the libraries on top of that. That's where all the action is these days. It's basically building blocks have become too low, and then everything else is kind of organized mess on top of that. Can you put more abstraction things that easy? I'm talking about research. This is one possible angle. I mean, you can think this unorganized mess is the right thing in there, because I think my feeling is what we do well is, when things get too complicated, we build abstraction layers. And the interesting thing there is we build this higher level programming language abstraction layer. And then now we have built so much CRUD on top of that without any nice abstraction layers. I think it's probably time to think through there could be other abstraction layers. Things like it's hitting, I mean, that is where parallelism is really hitting, because that layer, the object-oriented layer, doesn't really support that well. And it's all like kind of ad hoc on top of that. And so that says something. Yes, it's usable. It's like, yeah, I mean, we had this argument with assembly languages programmers for 2 decades. I mean, there are people who swear by assembly language. They could write it 2 times smaller, 2 times faster than anything you can write in high level language. It's probably still true today. But at the end, there were things that high level languages won out. I mean, I think we are probably in another layer like that. I don't know. I mean, we probably will go with that argument. You can always point something saying this is something you cannot do. There are still things like structured programs, unstructured programs. We talk about that. That argument went for a decade.
So the question I would pose is, can you formulate a kitchen sink language at a parallelizable level of abstraction?
That's interesting thing, because parallelization is one of the biggest things people have figured out is composability. You can't have two parallel regions as a black box put together. You suddenly run into deadlocks and all those other issues in there. Most of the things that you work is the abstraction works, because then you can compose at a higher level abstraction. You can have interface and say, here are something interface. I don't know what's underneath. I compose at the interface level, and then then the next guy composes at the higher level. And everything is hidden. We don't know how to do that in parallelism right now. Minute you combine two things, it's just like it runs into problems. And minute you figure that one out, if somebody can figure out what's the right abstraction that is composable, parallel abstraction, I think that will solve a huge amount of problems.
Isn't Fortress an attempt to do something that's parallelizable and the kitchen sink, but that then leaves all the parallelizable, saying how to parallelize?
I think
it's left on the programmers.
What I would say is right now is a very exciting time, because there's a big problem and nobody knows for the solution. And I think for industry, they lose a lot of sleep over that. But for academia, this is the best time, because we don't care. We don't have to make money out of these things. We don't have to get products out of it. But this actually have a very open problem that a lot of people cares about. And I think this is fun part because of that. I think there's a huge open problem that if you talk to people like Intel and Microsoft, a lot of people worries a lot about. They don't know how to deal with the future in 5-10 years time. They don't see this is scaling what they're doing. And from Intel point of view, they made money by making Moore's law available for people to use. And they don't know how to make it. They know how to make it available, but they don't know how to make people use it. From Microsoft point of view, their current development methodology is almost at its breaking point. I mean, if you look at last time, this happened in things like Windows 3, where their current development methodologies didn't really scale, and they really revamped it. They came up with all this process, and that had lasted till now. For the last two, Office and Vista, just realized they can't really scale that up. So they are already in trouble because they can't really scale. They can't write the next big OS that's 2 times bigger than Vista and hope to get it working. But on top of that, they have been thrown this multicore thing, and that really puts huge amount of money. So they are worried about that. So from both our point of view, everybody is clamoring for a solution. And things like last time round, I will talk about this in the future. Like last time round when that happened, it created huge amount of opportunities, and bunch of people who solved it kind of become famous. So they say, okay, we came up with a solution, and that people start using and stuff like that. Right now, everybody's kind of waiting for somebody to come up and like say, here's the solution, here's a solution. And there are a lot of, there's Fortress type approach is one, and what we are doing is one, and hopefully some of you will end up doing something interesting that might solve it. So this is why it's fun. I think we haven't had this much of an interesting times in programming languages, parallelism, architecture in last 2 decades. So with that, I stop my talk.